This is Official Nerd Business.
Hello nerd boys and girls. Welcome back to our programming series. Today we are taking a crack at Euler problem number 39. We will be using Python 3 in the PyCharm IDE. As you can see, I've already set up my boilerplate code, which has the following components. There's the title at the top. There's a line accepting a couple of parameters. In this case, there's only one parameter, which is perimeter. Try saying that 5 times quickly. Which has a default value of 1000. And there's a tag that doesn't really do much at the moment, but we might get into that soon. And here is the description of the problem itself. If B is the perimeter of a right-angled triangle with integral lengths A, B and C, there are exactly 3 solutions to make it all round in 120. There's the A, B, C of 20, 48 and 52. 24, 45, 51 and 30, 40, 50. And this one comes back to, if you divide each factor by 10, 3, 4, 5, that's the smallest Pythagoras triangle that we know. 3 squared plus 4 squared equals 5 squared. The same holds for 30 squared plus 40 squared equaling 50 squared. Find for which value of a p less than or equal to 1000 is the number of solutions maximized. So if we take any triangle in the range of perimeter length 3, 4, 5 is the smallest that we know of. So there's your perimeter length 12. Anything in the range 12 to up to and including 1000, when is it maximized? So for we would come along in that range, we would come along 120. And 120 has 3 solutions. Is there anything with more than 3 possible solutions where these numbers, 30 plus 40 plus 50, sum up to 120? So basically the question is, if we take any right triangle, so any triangle with a corner of 90 degrees and then 2 other corners, and we take the lengths A and B, we know that A squared plus B squared equals C squared. AB plus C should be 1000, or no more than 1000. So let's have a crack at it. And we're going to do that by picking A's, B's and C's to fit a given parameter. So I'm going to run through all possible parameters for perimeter in range. And we're going to start at 12. That's the smallest perimeter we could make with a Pythagorean triplet. And we're going to run up all the way to limit +1, and we're going to hit every single parameter in between. Now we want to know how many triplets we can generate for this particular valid triplets. Is an empty list at this point. This will hold all of our Pythagorean triplets. And we're going to have a current maximum. This is going to hold 2 values for us. I'm going to make a tuple with 2 elements. The first element is going to be the perimeter that gives us the maximum number of elements, and this is going to be the actual maximum number. So if this would hold more numbers than this tuple index 1 would hold, then we would substitute this one for this one with the perimeter up front. Alright. We're going to pick an A, which is anywhere in the range of 3 up to whatever perimeter we're currently looking at. This is overshooting it a lot. This is not going to leave much space for B's and C's, but whenever that becomes a problem, we're going to check a little later on, and we're going to cut out of this loop. And for B in range, let's assume that B is always bigger than or equal to A. And this is also going to run up to our designated perimeter. And then we're going to check. C is whatever is left over. So this is our perimeter minus A plus B. And if our C value is actually smaller than our B value, because I'm going to assume this is also strictly bigger than B, then we are going to break out of this loop. Now this is going to break so early on for bigger B's that this for loop is going to run out pretty quickly, and then it's going to fall back to here. Now, if we are still in the loop, we have an A and a B and a C that fit the perimeter, but we do not yet know if they are Pythagorean. That is, if A squared plus B squared equals C squared holds. So we're going to test that next. If our A squared plus our B squared happens to equal C squared, then we have ourselves a valid triplet. Valid triplets dot append A, B, C. Now note the double parentheses. I am making a tuple out of these three data elements and appending the entire tuple as one data element. So our list is going to have, if we were to hit 120, we're going to cycle through all possible A values. At some point we're going to hit 20. Then we're going to cycle through all possible B values. At some point we're going to hit a 48. And then we're going to check C, which will then default to being uh, 52. Our if statement will hold, in fact our second if statement will hold, and this triplet 20, 48, 52 will be added as one data element to our list of valid triplets. If we've seen all our A's and all our B's and then all our C's, we have a list of valid triplets. If the length of our valid triplets is greater than whatever current maximum holds in its one spot, then we want to set our current maximum to be a tuple of our current perimeter and the list of valid triplets themselves. A count of our valid triplets. You know what, let's just insert the list of valid triplets here and take the length of that when we are comparing it. It's a bit redundant, we could have taken the length once and stored it. For instance, if 500 is our current index at which we found the most fitting perimeters, and then the next one up is 700, then this is gonna take the length of this list of 500s 200 times. Well, I'm gonna spoil this a little bit, but this is not the most performant way we can do this anyway, so let's roll with it, and then let's just print out whatever is our current maximum and return. The question is for which index or for which total perimeter size this yields the most values. So that's in current maximum spot 0. So we're going to get that, return it. And this is all set up correctly, so we are going to run this. We're going to run this through MainPy to also get our timing information. I'd like to run number 39, please. Default input. Ooh. And we made some typo somewhere. Oh, right, I am setting this up to be an integer instead of an empty list or tuple. So, empty list. This should work a little bit better. Hang on, didn't start it through MainPy. This should work a little bit better. I'm gonna run number 39 again. Default parameter. It took us half a minute to run through all of our parameters and picking A's, B's and C's correspondingly, and we have found that the perimeter size 840 allows for 1, 2, 3, 4, 5, 6, 7, 8 different solutions. and that's our maximum. If you go over to Project Euler and you enter 840 as the solution to problem number 39, you will get a green check mark. However, we can improve greatly on the time of 28 seconds. So we're going to roll into attempt number 2 here. And for attempt number 2, we're going to use a little bit of math that we saw already in, if I'm not mistaken, problem number 9. Attempt number 2, taking a limit. And in the special Pythagorean problem number 9, we already saw that we can pick two values, m and n, and use those to calculate a Pythagorean triplet for us. The thing is that currently what we're doing now here is we're just picking numbers and then checking if those are a Pythagorean triplet. And we can do better than that by running through m and n, always getting Pythagorean triplets and checking if those fall within our parameter limit. So we are going to do just that. This is going to be a list, and this too. I'll show what these do in a second. I'm going to set up a loop here for m, which is going to be a semi-infinite loop. Also going to set up an m and n here. These are 2 and 1. I think these are good starting values. There were a set of formulas that if you enter m and n as two independent variables and use them in 3 specific ways, you'd get 3 values that are always Pythagorean, have these Pythagorean relationship of a squared plus b squared being c squared. And you can go back to problem number 9 to check out those formulas. But they were, knowing that m is always strictly bigger than n, it's m squared minus n squared 2 times m times n, and m squared plus n squared. This will always give us, in fact, let's check it out. It's 2 squared, which is 4, minus 1 squared, which is 1. This gives us a 3. 2m and n gives us 2 times 2 is 4 times 1 is still 4. And so we have a 3 and a 4 in our a and b, and we can kind of guess what c is going to be then. M squared is still 4, plus n squared is still 1 is 5. So here's the formula that's going to give us our Pythagorean trips. And now we're going to check if a squared, or if a plus b plus c is greater than our limit, then we've exceeded our perimeter. We want to, by the way, we want to increment m by 1. And we want to add whatever this generated to our list of triplets. Not yet, by the way, only if this did not exceed our limit. So we are going to take generated trips. We're gonna append with a triplet of A, B, and C. Well done. If we exceeded our limit, then we're gonna set n to be n plus 1, and we want to set m to be n plus 1. We're gonna reset the loop with slightly different variables. So we've checked out all the ns1s with m raising up until this no longer satisfies our parameter criterion, and then we're gonna drop back. We're gonna make this into a 2, this into a 3, and then gonna run back up again. But I said that this loop is gonna be semi-permanent. So we are gonna check if we did not generate any triplets on our last run, then our base m and n are too big. Yes, our base m and n are going to be too big for zero. Then we're going to break out. We are no longer in the zone where our m and n, are going to give us anything valid for this within this parameter. And alright, this is a valid triplet, and else you want to shift all of the generated triplets into total trips. And reset generated trips into an empty list again. So this should give us a lot of Pythagorean triplets within our parameters in absolutely no time whatsoever. Let's have a look. Generated trips, no total trips. I want to see total trips. And we're going to set this up to run not attempt number 1, but attempt number 2. Alright. I'm going to run this file solo, not through main.py. And this does give us a lot of Pythagorean triplets. There's 3, 4, 5. However, we've lost one bit of detail, and that's keeping track of which perimeter size this is for. So we're gonna go back and redo that. I'm gonna make a dictionary. This is for every perimeter. Now I'm gonna run through every triplet in total trips. And I'm gonna add these to our dict. The key here is gonna be sum of the trip. In fact, I'm going to make a variable s out of that. If s in dict param, then I want to take this element and it's going to be a list, so I want to append this particular triplet to that list, and else we are going to set this up And this is all going to print on one line. I don't want that. For x in print x. I'm not entirely sure if this. I'm always confused if this gives me keys or values. I'm expecting keys, and it's keys. All right. So let's have a look at our dictionary now. Right, so it has triplets for almost every perimeter. Sometimes even 2. So here's our example 120, which, let's see. Wait, where did you go? Hang on, where's 120? Oh, nifty. Oh, they're not exactly in order, are they? Let's see if we can fix that. Yes, that's fixed. Here's 120. But there's only one solution for 120. And that's because the formula we've used only generates primary category in triplets. And there's more triplets possible. Namely, if we multiply every A, B, and C by the same number, then we would get another triplet. Here you can see it. For 120, there's the triplet 30, 40, 50, which is 3, 4, 5 times 10. So there's also a Pythagorean triplet 3, 4, 5 times 2, etc. So we're gonna, I think we're gonna extend this loop to hold that information. And I'm afraid this is not going to be particularly pretty. So I'm going to create a vector and a new trip. These are 1 and then this is going to be dependent on new trip, and this is going to be dependent on new trip. If we don't change anything about this code, we should still get exactly what we have right now. Not quite. Let's see if we add a cast tuple to this. It's not too happy about us one-lining this, so we're gonna break it up. Alright, this is pretty much the same as we had before. However, now we're gonna do this while s is less than or equal to limit. Get. We're gonna regularly add this to our dictionary, and then we're gonna increment factor by 1. And then we're gonna recalculate this using the factor and the original triplet. And then we're gonna recalculate this by resumming everything and checking if this still falls within our limit. So this should expand every triplet we have by factor 2, then by factor 3, then by factor 4, as long as the new combination, just so calculated over the new factor, stays within our limit. So let's have a rerun of this. And now we can see that there are quite some contenders for longest. 840 should still be king of the hill, which it is not. I think we're hitting the same value a couple of times here. Yeah, we now have duplicates, so we need to deduplicate everything in. This is there are two separate primary Pythagorean triplets, which when multiplied by 4 and when multiplied by 6 give us the same multiplied Pythagorean triplet. So we can fix that for d in dict param param at index d is the set version of whatever is at dict param index d, and that should deduplicate our everything, which it does nicely. So 960 still is has quite a run, but 840 is now again king of the hill. So that's our deduplicated collection, and at this point, while we're running through it anyways, we can again install the current maximum, and wait, I'm gonna put those completely at the top. They are scorekeepers in this method and should not interfere with the calculations here. And again, I'm not gonna reprint the dict here. I'm gonna basically do the same as we did here. I'm gonna print current maximum and return current maximum index 0. Now that our set is our entry for perimeter D is deduplicated, we now can compare lengths. So if the length of dict perimeters index D is greater than the length of current max index 1, then we can override current max with a new tuple of D and dict params D. I'm going to reload MainPy, run 39 solution 2, default parameter, and it took us way less than 1 second to come up with the same answer as we previously had in half a minute. This is one of the biggest performance boosts we've had so far. And that's it for problem number 39. I hope you've enjoyed it. Next up is problem number 40, and I think having 40 videos on Project Euler is a bit of a milestone, so I think I'm gonna come up with something special for that particular problem. I will see you again next time. Thanks for watching.
Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.